Now we're after the time required to produce a single batch in the batch reactor that we designed. And we know that our goal is to produce 21.9 metric tons per day of Teflon, and we knew that corresponded to our overall goal of 8,000 tons per year. Now we need to derive an equation in terms of time and the parameters that we know. Let's remind ourselves that we do know the concentration, we know the volume, and so we can start off with the general mole balance. It says in minus out plus net generation is going to be equal to accumulation. You know, this is a batch reactor. There's nothing coming in, there's nothing coming out, and we know that accumulation would be the rate of change of moles with respect to time. And that the net generation term would definitely then be equal to the rate of the reaction multiplied by the volume of the reactor. That gets us one equation here. Label that 1. Now, we also know that the amount of moles at any time in the reactor is going to be equal to the initial amount of moles minus how much was converted multiplied by that initial amount of moles. We take the derivative of that with respect to time. We're going to be left with, well, we know that's a constant, so that goes away, minus NA0 dx over dt. Here we have another equation that we can actually combine with equation 1, divide throughout by this volume term, and recognizing that concentration, or that initial concentration, is going to be equal to that initial amount of moles divided by the volume. When we do all of that, we are left with an overall rate law that says it's equal to the initial amount of concentration multiplied by the rate of change of conversion with respect to that time that we are after. Now that we're after time, the time parameter here, we know the initial amount of concentration and we know the conversion. So really the only thing that's stopping us from integrating this equation and finding that time is information about the rate law. Now we find this information about the rate law just doing some chemistry research behind polymerization reactions. We found that the rate law is actually broken up into 3 steps: the initial step, the propagation step, and a termination step. And they each have their individual rate laws associated with their step. And so the idea was to combine all 3 of these steps and get a net rate law for the polymerization reaction. That's the reaction in that batch reactor. And so I'll just show you one. So let's say the initial step, that rate law, let's call it VI, is going to be equal to 2 multiplied by a parameter F. We'll get into detail on these variables in a second. Multiplied by KD, multiplied by CI, which is the concentration of the radicals in the solution. That's also a parameter that we set. So that's known. This is a constant. That is a constant. Actually, these 4 constants actually define all 3 of these steps, and they can all be looked up and found in appendices / Perry's handbook or other sources of information on these types of reactions. Now, combining these steps and plugging them into that rate of reaction term right here, we would be left with an overall expression that looks something like this in terms of time. Apologize for my bad handwriting. negative Kp multiplied by 1 minus the conversion multiplied by 2 times those same constants that we were talking about in this a little while ago, multiplied by Ci, all raised to the 1/2 power. We can now solve this analytically and come up with a solution that gives the time would be equal to natural log of 1 minus x divided by Kp multiplied by 2 times F times Kd divided by Kt times Ci. And that all raised to the 1/2. And again, we know the conversion is 0.9. We know that all of these values, the Ci, the concentration of the radical, is set by the operator. We know that the Kd, Kt, F, Kp terms are all found in appendices. So that's how you would find that.